In this lesson, we will learn about summation notation. So summation notation is essentially telling us to take the sum of all of the items in a series. There are, of course, infinite series and then finite series, just the way that we talked about before. Infinite meaning that it would go on forever, finite meaning that it would end at some point. And so I want to point out a few things about this summation notation. The bottom here tells me what the index is. Not the index is in square root, but we call that an index as well. So this is saying that the first term will be a 1, and it will go on to infinity. So a sub 1, a sub 2, a sub 3, etc., all the way on to infinity. Notice this one is different because this upper bound, so the lower bound is still 1, but the upper bound is n, meaning that my last term is a to the n. So obviously, normally there will be a number here as opposed to a variable. This will make much more sense when we're doing this. So looking at this first one, and again, this looks a little bit different than it did on the last screen, because on the last screen we had the k equals 1 below it and the 4 on the top. It doesn't matter if it's above and below or to the side like this, they mean the same thing. So what this is telling me is to start at 1, which means 2 times 1 minus 1, and then add the next digit up, which is 2 times 2 minus 1, and then add the next digit up, which is 2 times 3 minus 1, and then add the next digit up, which is 2 times 4 minus 1, and notice 4 is where I would stop. So then I'm going to add all of these values together. So 2 times 1 is 2, minus 1 is 1, that's 4 minus 1, that's 6 minus 1, that's 8 minus 1. I'm going to add all those together to get 16. So that's all it's telling me to do, is to start at 1 and go up to 4 and stop, and then add those together. For my next, I'm starting at 1 and going to 3. So this is 4 times 1 over 1 squared, plus 4 times 2 over 2 squared, plus 4 times 3 over 3 squared. So that gives me 4. And this is 8 over 4, which is 2. And this is 12 over 9, which is 4 over 3. And then I would add all of those together. So this is 6, which is 18 22 thirds, is how I would write it as an improper fraction. And again, I just took the 6, I took it times 3 to find out how many thirds that was, which was 18. I added the 4 thirds I already had, so I have 22 total thirds. Typically, we would write it as 22 thirds as opposed to 7 1/3, because 22 thirds tends to be easier to work with down the road. Last one, we're starting at 3 going to 5. So I've got negative 1 to the 3 plus 1, which is 4, times 4 times 3, plus negative 1 to the 4 plus 1, which is 5, times 4 times 5. Oh, just kidding. 4 times 4. Got distracted by the 5. And then negative 1 to the 5 plus 1, which is 6, and then 4 times 5. So negative 1 to the 4th gives me a positive 1. So that's positive 1 times 12, which is 12. This would be a negative 1 and 16, so that's negative 16. And this would be a positive 1 again and 20. So adding all of those up, I arrive at 16. Here are 3 for you to try, so try all 3, then press play to check your work. For the first, again, we haven't done one like this. This one's a little bit tricky because, as you can see, there's no k value in the expression. So what this means is, for the first one, I'm having a 7, and for the second one, it's a 7, and for the third one, it's a 7, and for the fourth one, it's a 7. So that gives me a total of 28. The shortcut there is to basically take however many you're going to have, in this case 4, multiplied by that constant. For the next I'm plugging in 1, starting with 1, so 1 plus 1, which is 2 squared. I'm plugging in 2, so 2 plus 1, which is 3 squared. And I'm plugging in 3, so 3 plus 1, which is 4 squared. So that's 4 plus 9 plus 16, which is 29. And the last one, starting at 3, going to 5, I have 1/2 to the 3 plus 1, and then I have 1/2 to the 4 plus 1, and then I have 1/2 to the 5 plus 1. So lots of fractions on this one. Remember, when you're taking a value to a power, you're taking both the numerator and the denominator to that power. So that would be 1 over 16 plus 1 over 32 plus 1 over 64. And then, of course, to add all of those together, I would need a common denominator. So I would take this times 2 on top and on bottom. And I would take this times 4 on top and on bottom. And I would end up with 4, 5, 6, 7, 64ths. The other thing we want to practice with summation notation is to take a sum like this and to be able to write it in summation notation, which will help us in an upcoming lesson. So again, what I'm looking for here is a pattern. And it looks like the pattern is that the denominator is always 5. Even on this one, this is 2, but if I'm using this pattern of 5, this is actually like 10/5. So even though they wrote it as a 2, it's 10/5. So it looks like my pattern is that there's a 5 on the bottom, and on the top, it's multiples of 2. So that would be 2 times I, because if I is 1, that would be 2 times 1, which is 2. And if I is 2, that's 2 times 2, which is 4, etc. Which means my summation starts at 1 and goes to 1, 2, 3, 4, 5. So this would be the way that I write it in summation notation. Looking at this pattern, this is 1/3, and then 1, 3, 9, 27, 81. These are all base 3 numbers. So it looks like it's 3 to the I. Notice 1/3 could be written as 3 to the -1. 1 could be written as 3 to the 0. This would be 3 to the 1st, 3 squared, 3 cubed, 3 to the 4th. So that means this is the summation starting at -1 going up to 4. Last one, a little bit trickier. I've got -3/4, 9/16, -27/64, 81 over 256. So again, notice that it's alternating, which means it's going to be a negative. And you can either write it with that -1 or just put the negative on the fraction. It looks like I'm taking 3/4 to the first power, to the second power, to the third power, because this looks like -3 over 4, and then 3 squared over 4 squared, and then -3 cubed over 4 cubed, and then -3 to the 4th, 4 to the 4th. So I'm taking -3/4 to the I power, starting with 1 and going to 4. Here are 2 for you to try on your own, so try them both and then press play to check your work. For the first, we actually have a little bit of a cheat here, because if you're trying to find the pattern here, obviously this is increasing by 1. Well, that's where this n plus 1 comes from. And this is obviously multiples of 3, so notice 3n. So this is a little bit different than what we're used to, but this one would be the summation starting at 1 and going until n, because notice my last term is n plus 1 and 3n, of I plus 1 factorial over 3i. So again, if I plug in 1, I get 1 plus 1, which is 2 factorial, and then 3 times 1, which is 3. If I plug in 2, 2 plus 1 is 3 factorial over 6. So we can see that that is the correct summation. For the other, we've got kind of a lot going on. So looking at the numerators, this is all perfect cubes. So this is 1 cubed, this is 2 cubed, this is 3 cubed, and this is 4 cubed. We also have that we have alternating signs. And we also have that this is 5 to the first, 5 to the second, 5 to the third, 5 to the fourth, etc. So my summation is going to start at 1 and go until 4. And I'm going to take -1 to the I. Now the reason that I'm doing that is because that's another way to write it if the signs are alternating. Because on the I squared, or the -1 squared, that would give me the +1, and notice the second term is in fact positive. The other thing I need to do is relate I to what's happening in the fraction. So this is 1 to the third, 2 to the third, 3 to the third, 4 to the third. So that means it's I to the third, and the denominator is 5 to the power of I. So that is what we're looking at. Now, another way that I could have done that is I also could have written the negative on the 5 in the denominator, and that would have done the exact same thing.